How are aerogels made? Polymers and composites. Imagine a material so light that it could almost float in the air, yet so strong that it can insulate against extreme temperatures. That's what aerogels are all about. They are highly porous, lightweight substances created through a fascinating process that preserves their tiny, intricate structures. Let's explore how these amazing materials are made, especially focusing on polymers and composites, and what makes them so special in the world of material science. The process begins with creating a gel, which is a network of tiny particles suspended in a liquid. For silica-based aerogels, this involves a chemical reaction called sol-gel synthesis. Silicon alkyd compounds like tetraethyl orthosilicate are mixed with water and catalysts. This mixture undergoes hydrolysis and condensation reactions, forming a wet gel that is filled with liquid inside its tiny pores. When making polymer aerogels, similar reactions occur where monomers link together to form a cross-linked polymer network, resulting in a gel. Next comes the solvent exchange step. The wet gel's pores are filled with the original liquid, often alcohol or water. To prevent the delicate structure from collapsing during drying, the liquid inside the pores is replaced with a more suitable fluid, usually liquid carbon dioxide. This is done by washing or exchanging the solvent multiple times, ensuring the gel is ready for the drying process. Drying is the most critical part. The goal is to remove the liquid without damaging the gel's nanostructure. The most common method is supercritical drying. The gel is placed inside a pressure vessel, where liquid carbon dioxide replaces the pore liquid. The vessel's temperature and pressure are then increased beyond carbon dioxide's critical point, turning it into a supercritical fluid. In this state, the fluid acts like both a liquid and a gas, eliminating surface tension that could cause the structure to collapse. Slowly venting the carbon dioxide leaves behind a dry aerogel that retains its porous, nanostructured framework. For polymer and composite aerogels, the process adapts by including polymer precursors or fibers during gel formation. Polymer aerogels are made by polymerizing monomers into a gel network, then drying it similarly to silica aerogels. Composite aerogels incorporate reinforcing fibers or particles during the gelation process, which helps improve their mechanical strength and tailor their properties for specific uses. Since aerogels are naturally fragile due to their high porosity, scientists work to strengthen them. They do this by adding polymers or crosslinkers into the gel network, creating composites with fibers or nanoparticles, or modifying the precursors for more uniform pore structures. Post-processing treatments like annealing can also improve durability. Scaling up production involves overcoming challenges like maintaining uniform pore sizes to prevent cracking and designing equipment that allows for efficient solvent exchange and drying. Industrial methods often use large autoclaves with multiple inlets and outlets to ensure even processing. Efforts to reduce costs focus on developing ambient pressure drying techniques and continuous production lines, making aerogels more accessible for practical uses. In the world of mechanical engineering, aerogels are used for thermal insulation in spacecraft, buildings, and electronic devices because of their low thermal conductivity and lightweight nature. When reinforced with polymers or fibers, they become stronger and more impact-resistant, opening doors for their use in load-bearing parts or impact protection. In summary, aerogels are made by forming a gel from polymer or silica precursors, carefully exchanging the solvent, and drying under conditions that preserve their tiny, porous structure. Adding polymers and reinforcements creates stronger, more versatile composite aerogels. This process combines chemistry, physics, and engineering to produce materials that are both light and tough, perfect for a wide range of innovative applications.